Something is detonating in the empty space between galaxies. Explosions as powerful as kilonova events, happening where no stars exist to produce them. And every explanation scientists reach for keeps running into the same wall. The physics that should govern these explosions does not fully match what the telescopes are actually recording. A kilonova is one of the most energetic events in the known universe. It occurs when two neutron stars, the ultra-dense collapsed cores of dead massive stars, spiral together and merge. The collision releases an enormous burst of energy across multiple wavelengths, from gamma rays to optical light, and it produces heavy elements like gold, platinum, and uranium through a process called rapid neutron capture, or the R process. The first directly confirmed kilonova was GW170817, detected in August 2017 simultaneously by gravitational wave detectors LIGO and Virgo, and by dozens of telescopes worldwide. That event was located inside a galaxy, associated with the stellar population that produced the two neutron stars in the first place. But now astronomers are detecting kilonova-like explosions, events with similar energy scales, similar time scales, and similar spectral signatures, in locations where no host galaxy is visible. These are called hostless, or host-deficient short gamma-ray bursts, and they represent one of the most puzzling observational problems in modern astrophysics. Short gamma-ray bursts are flashes of high-energy gamma radiation lasting less than 2 seconds. They are widely accepted to be produced by neutron star mergers, the same events that produce kilonovae. Detecting one in empty intergalactic space is deeply strange, because neutron stars form inside galaxies, inside massive stars that live and die within stellar populations. For a neutron star pair to end up in empty space, something unusual has to have happened. The leading explanation involves a kick. When a massive star collapses into a neutron star at the end of its life, the supernova explosion is often asymmetric. It does not fire perfectly evenly in all directions. That asymmetry gives the newly formed neutron star a velocity kick, launching it in one direction at hundreds of kilometers per second. If a binary system, two stars orbiting each other, both undergo supernova and both receive kicks that happen to send the resulting neutron stars in the same direction, the pair can be ejected from their host galaxy entirely before they spiral together and merge. The time for two neutron stars to merge after formation, called the merger delay time, can range from tens of millions to billions of years. During that time, a kicked binary moving at several hundred kilometers per second can travel enormous distances. At 500 kilometers per second over 1 billion years, a neutron star pair can travel roughly 500 kiloparsecs, well over 1.5 million light-years, far enough to be completely outside any visible galaxy when they finally collide. This explanation works in theory, and it accounts for some host-deficient events. But the problem is that the rate and distribution of hostless events does not perfectly match what kick velocity models predict. Some events appear too far from any plausible host galaxy. Some have afterglow properties that do not fit cleanly into the kicked binary framework. And some of the optical counterparts, the kilonova-like signals detected in visible light, show characteristics that are still being actively debated. In 2023 and 2024, several teams published detailed afterglow analyses of short gamma-ray bursts detected by the Neil Gehrels Swift Observatory and Fermi Gamma-Ray Space Telescope. Some of these events had deep follow-up imaging that revealed no host galaxy even with the most powerful ground-based telescopes available, including Keck and the VLT. The absence of a host down to extremely faint magnitude limits makes the kicked binary model increasingly stretched as a universal explanation. There is also a competing hypothesis gaining attention. Some short gamma-ray bursts may originate from compact star clusters, ancient globular clusters that have drifted to the outskirts of galaxies or into intergalactic space, where dynamical interactions between stars increase the rate of neutron star binary formation and merger. Globular clusters are old, dense, and gravitationally complex environments where close encounters between stars can create binaries that would never form in isolation. Whatever the mechanism, the physical consequence is the same. Heavy elements forged in the fire of merging neutron stars, gold, uranium, platinum, are being scattered directly into intergalactic space rather than into the interstellar medium of galaxies. That changes how we model the chemical enrichment of the universe and where the heavy elements that eventually end up in new solar systems come from. Follow for more on the explosions that are rewriting what we know about the universe's chemistry. And tell me, the fact that gold and platinum are forged in neutron star collisions happening in empty space between galaxies, does that make those elements feel more rare or more extraordinary to you?